Hello, my name's Josh. Um, our second project asks us to design this optimal rocket ascent. Um, our tasks are to model the dynamics using like ODE 45, use plots to interpret results, and test at least two strategies, and explain which one receives a higher altitude. All right, I want to bounce over to my code now. All right, now I'm just sharing my screen so you can get a little better look at what I've got going on here. To start off the code, we have my givens, or like your initial stuff that we were given in the problem statement. So our mass, our velocity, altitude, dry mass, max thrust, impulse, coefficient of drag, density of air, and our rocket's cross sectional area, and also like gravity. Moving on, we have this is for our ODE function right here, our ODE functions, because we're doing two different ones for there are two different strategies. So our initial state vector is just going to use our initial height, velo, and mass that we were given in here. Our first strategy is to have thrust until we empty out all of our fuel, which would be most optimal because uh, since this is like a model rocket, I'm assuming we're using solid fuel and there's no way of throttling. So it's pretty much just the thrust increasing or decreasing, or the thrust increasing until it maxes out. And we use that max thrust um, over a period of time to make our impulse. Uh, yeah, without any throttling, so it's just kind of like constant. So if you just burn fuel until it's empty, which gives you the most thrust and least amount of most thrust slash impulse and the least amount of mass because you empty out the fuel. That's probably going to be the most, or that is going to be the most optimal method to get the highest uh, altitude. Um, so that's my first strategy. We use our thrust function. Um, this is just like our ODE right here. Um, function of velocity here. Position, change of position, velocity with respect to time. Um, this is our change in velocity or acceleration, and this is our change in mass from our given equations, like our fuel consumption, how it changes our mass. Then we solve for time using our ODE 45, with our first ODE, and then our interval of time, and our initial state vector with our position, height, and mass. And this Y1 here is just pretty much like it's sort of like a state. So we grab our H1, V1, and M1, our new height, velocity, and masses from this like state array. Yeah, and it's four plots. Our second strategy, same kind of thing, except same like methodology here, except we're changing how we um, do this. And yeah, all this is the same too. But it's different if you have this formula we made called burn time. And all it is integrating our mass variation formula. Um, so now we're decreasing the thrust linearly to zero using our burn time equation. As you can see, that's us using burn time to linearly decrease it to zero. Same velocity, same acceleration, pretty much, and then same change in mass, kind of. Seem like change in mass and velocity, like set up here. As you can see, we got our velo, acceleration, and then mass. Here we have our velo, acceleration, mass. Except here we use our our T2 and our T1 are like our main differences. And then same sort of extract or not extraction. This is the extraction. Same way of solving using ODE45, except we plug in diffie-Q2 rather than diffie-Q1. Same time interval, and then same initial height, mass, and velocity. Yeah, and then we grab our values of velo, mass, and height for our plots. And then plotting. It's just basic plotting. We have three different plots, so it's kind of easier to look at it. You can do it all in one because all of it's with respect to time. So you could just keep a single time on your x-axis, and then instead of having a unit on the y, you could just have numbers ranging from like 0 to 1,000, and have each line name kind of like what we use on our Open Rocket software in MSP. But yeah, just basic plotting, time. So for our first strategy, it's altitude versus time. So we're going to use T and H, time and height, and then T2 and H2, the different color line. And then yeah, pretty much same thing here. And yeah, same thing here, except with mass and velo on these two. So now I'm going to plot these and bounce over and talk a little bit about the plots. Okay, thank you. So as you can see in our figure, so we're doing mass versus time, just to check that we don't go below that 1 kilogram. So for our first strategy, because we burn it all of our fuel, we go down to the 1 kilogram. Our second strategy, since we go down to zero thrust, we linearly decrease to zero thrust. We actually don't use all of our propellant, and we're down to about 1.25 kilograms. So definitely less efficient, and you'll see this in the velocity and altitude plots. So let's bounce over to those next. So as you can see in our velocity versus time, our first strategy, we hit a peak velocity of around 80 meters per second. But with our second strategy, we hit about 45. So a little over half. And that's just because the using thrust to decreasing thrust to zero linearly, it doesn't burn all the mass. It doesn't, and by not burning all the mass, you don't use all your propellant, which also hurts your velocity and apogee, which is another word for your max altitude. Yeah, not using that propellant jeopardizes your efficiency quite a lot, as you can see here. Even at this time, like at 5.06 seconds, we're at 45 meters per second here. If we projected up to here, we're about 65. So just not nearly as efficient. And next, I'll bounce over to our, well, first, actually, the ascent time for the first strategy, I got to mention that, is about um, 12 seconds to our peak velocity. Um, and around 5 for our peak velocity of Strat 2. All right, on to the altitude. So on our altitude versus time plot, you can kind of see and understand the biggest difference if you're not really in rocketry. Um, our first strategy took us to an apogee of about 890 meters, whereas our second one took us about to 395. Um, so the ascent time to get to apogee would be about 13 seconds, yeah, versus 17. Um, and that's just because we didn't burn as much propellant here. Why is this doing this? Okay, well, whatever. I don't know why my mouse is doing that, but the total flight time to where it hits back to zero for the second one is about, for the second strategy is around 25 seconds ish. I'm getting 24 seconds. And for the first strategy is 40 seconds. Also, just because it goes way higher, takes longer to descend. It also peaks like 4 or 5 seconds later, which would explain this. Yeah, pretty much that second strategy just isn't as good because it doesn't burn all the fuel. So you're holding more mass and you're also wasting propellant that could be taking you higher. And yeah, that's all I have. Thank you.